Okay, next we are going to talk about the Groundwater Data Mapper application and its associated tools. So this is another Tethys application, and it's part of the GeoGlows apps.geoglows.org portal. And it's one of the two main groundwater applications alongside the GRACE groundwater subsetting tool. And the Groundwater Data Mapper allows you to upload wells and historical water level measurements for a set of aquifers or basins in a particular region. And as such, it serves as an online database of your wells and your water levels. And you can select different aquifers and view the wells in each aquifer. If you click on a given well, it shows you the time history for that well and the metadata about the well. It allows you to look for outliers in your well data and allows you to compare how the water levels are changing in different locations across your aquifer. And it can also be used to generate maps of water levels, and those can be time varying maps, so it can show how your water levels are evolving or changing over time. And furthermore, it can show how your groundwater storage is changing over time. So it's a really powerful tool for water managers to determine what is happening with their groundwater storage. Is it being used sustainably or not? And what are the long-term trends in the groundwater storage change? And this process of calculating the storage change or calculating the water levels. So again, we take well locations and combine with that a set of historical water level measurements in a table. We then use time and space interpolation algorithms that are informed by Earth observations through machine learning, and we end up with maps showing how those water levels change over time. So next we're going to dig into that and look at each of those steps in that process more carefully. Step number 1 is impute gaps in water level time series using machine learning and Earth observations. So the issue here is, in many cases, historical water level data can often have long gaps of many years without a measurement. So for this well, there were a couple of measurements back in, say, 1974, and then from 1974 through almost, let's see, 1998 probably, there aren't any measurements, and then there are a series of measurements. And down here, you have a lot of data over a short period, but nothing back here. And so this is fairly common, and some agencies have fairly complete water level records, but it's much more common to have gaps, large gaps, either between data or on before or after the measurements are taken. And so one of the ways we can deal with that is so the challenge is to try to infer what happened during these gaps or periods where the water levels were not taken. Is there a way we can reliably come up with an estimate for that will help us build these water level maps in a way that's more accurate than we could do otherwise? And so one of the things we take advantage of to do this is that water levels in wells can be correlated in some cases to remote sensing data. So this is the geodas, or excuse me, at the top here, we're looking at the water level at a particular well, And on the bottom, we're looking at the variation of soil moisture from GeoDAS, the NASA land surface model that we talked about in the other presentation on the GRACE groundwater subsetting tool. And if you look, so the periods in red are when it's dry, below normal soil moisture, and where it's blue, it's above normal. So we have a drought period here, which led to a decline. Then we had a series of wet years, which caused it to rise, and then some kind of average years, so it's fairly flat. And then a rise here, and then a steady decline over this extended drought period. So, in other words, when you have a wet period, you get more recharge to an aquifer, and you don't have to pump your wells as much because you have sufficient surface water. And when you have a dry period, you tend to pump more water and you get less recharge, causing the water level to go down. So if we can look at correlations between something like soil moisture and the water level in a well, then we can use that to help infer what happened when we don't have measurements. And so what we do is we use a machine learning algorithm to find those correlations between the water levels and the wet and dry periods, the soil moisture. And then we use that to infer what's happening when we don't have data. So here this orange plot is where we do have data, measured data, and then using the machine learning algorithm and this correlation. So looking at this data here, we learn the correlation between the soil moisture and the water levels, and then we can use that to predict what the water levels probably look like over this period where we didn't do the measurements. And then, once we do that, once we have this complete record, then we, let's say we want to do a map of the water level at each year. We just, at each year, we pick off the water level from either the imputed or the original data. And that gives us a series of water levels at each well, which we can then use to interpolate to get, we do that every year, and then we get a series of water levels which we can animate to visualize how the water levels change over time, and we can also do some other kinds of analyses with this. So the output from this process is a series of rasters that vary over time. So once we have this set of time-varying rasters, how do we go about calculating groundwater storage? To do that, if you look at a cross-section through this water level map, and let's say that this would be the shape of that water level, that water table map at some period in time, and then we look at that at a later period in time, and it may have a different shape. Let's assume in this case that the water levels go down. If you calculate the volume between those two rasters and then multiply that by a storage coefficient representing the fraction of the void space in the aquifer matrix that's occupied by water, you can then have a pretty good estimate of the change in groundwater storage. And if you string those together, you get a time history of groundwater storage. So let's look at an example. We've taken the data from Cuba, which was provided to us, and uploaded it into the groundwater data mapper. And of the different polygons, aquifer polygons we were given, we aggregated them into some larger regions. And when you again you upload the data in the groundwater data mapper are organized in kind of a hierarchical fashion. First of all, there's a region. In this case, the region is Cuba. And then within that region, you have a series of what we call aquifer polygons. And these could be basins or, small or large aquifers. It's where you want to do your analysis and organize your wells. And then in the application, you can select an aquifer using this selector, or you can actually just click on it. And then you select a variable. You can, the most common variable, of course, is the water table elevation, but you can also use salinity level as a variable, or depth to groundwater. And then, and so in this case, this next slide, we've selected one of the regions. This is the Ciego region, which I believe is right here. And here are the wells in the region. Some of them span just a few years, and then some of them span, in this case, about a 40-year period. And it has a pretty consistent long-term record that you wouldn't really need to do any gap filling or imputation on this particular water level record. But again, if you click on the click on a well, it shows the time series for that well. And then this is a time varying raster. If you click use these animation tools here on the bottom, you can animate that. And there's a legend showing how those colors correspond to particular water levels. And you can, again, explore this for each of the aquifers in the region. And if you click on it, when you have a raster that's been processed, if you click on this View Drawdown Volume button, it brings up this map, or excuse me, this plot of the change in storage over time. I believe this is millions of cubic meters, I believe, for this. I'd have to double check on the units that were used here, but in any case, it shows for this. In this case, the water storage is pretty constant, and then starting about 1998 or so, the storage went up and then back down. And this is just for one region. It's just for the Ciego region. And we could do this for each of the regions in Cuba. Another thing that you can do, which can be really beneficial, is there's a multiple well select feature, and then you can drag a box or use a polygon to select a set of wells, or just hold down the shift key and select wells. And then when you click Get Values from Multi-Select, it brings up a plot showing a time series for all of the wells that are selected. So what this tells us is, in this box here, most of the wells only have data from about 2020 to 2025, but there are 2 wells in this region that have much longer periods. So when you select multiple wells, it's a really nice way to do comparisons and look at long-term trends across multiple wells. Everything associated with the groundwater mapper is thoroughly documented at this website, gwdm.readthedocs.io, and it can be displayed in different languages, in Spanish and French. This talks about not just the mapping algorithm I described, but also how to organize your data, how to format the data for uploading, and how to go about uploading your data into the groundwater data mapper, and then how to visualize it. Thank you.